Good morning to everyone. Firstly, I would like to welcome the committee and everyone who attends my PhD defense here at the Polytech Sofia or remotely. Thank you very much for your participation. For the past 3 years, I had a great pleasure to follow a PhD funded by the Direction Générale de l'Armement and by the Agence l'Innovation de Défense. The title of my thesis is Joint Source Cryptographic Channel Coding for Secured Real-Time Voice Communications on Voice Channels. My name is Krasnowski and my PhD was supervised by Professor Bruno Martin, Dr. Jérôme Lebrun, and by Thierry Pless, all of them being the members of my committee. Thank you once again for evaluating my work. The goal of my PhD was to design, develop, and validate new speech encryption algorithms. At the beginning of the presentation, I will introduce you into my research topic and I will show some relevant research questions. Then I will describe my 3 different contributions: new data over voice technique, distortion-tolerant speech encryption, and a dedicated key exchange protocol. Finally, I will conclude the presentation. During my PhD, I was working on a specialized device for speech encryption. This device is supposed to be more secure than voice over IP and at the same time to be cheaper than cryptophones. Below, you can see a schematic of a secure communication. In this setting, we use a headset with a microphone. Firstly, our voice recorded by the headset is forwarded to the voice encrypting device. This device encrypts speech in real time and produces a synthetic pseudo-speech signal in the audio domain. This encrypted signal is forwarded to the microphone of a mobile phone. The mobile phone treats this encrypted signal as ordinary voice and sends it over a voice channel with compression. Finally, the received signal is decrypted by the paired device with a corresponding cryptographic key. The big advantage of this setting is that we are secured against spying malware installed on the mobile phone. It is because the encrypted signal that enters the mobile phone is already secured. Furthermore, it should be hard to hack the voice encrypting device remotely because it has only 2 analog audio interfaces. Of course, we assume that all other external microphones of the mobile phone are somehow blocked. For example, in the right figure, you may note that the mobile phone is covered by a special case. Another advantage of this setting is that we are not constrained to a particular voice channel and communication can be done over Skype, WhatsApp, frigicalls or analog links. From the previous slide, it is clear that the crucial element in this scheme is the voice encrypting device. However, what happens inside? It is helpful to think that this device performs a chain of operations. Firstly, the input speech is compressed into a binary form. Next, the compressed vocal parameters are scrambled by some enciphering algorithm. In the third step, we apply some error protection mechanism to protect against channel distortion. Finally, the resulted binary data are encoded into an analog signal that resembles pseudo-speech. The above approach is very popular in the telecommunication domain. However, as I will explain later, this block-based system is really not adapted to voice channels. For this reason, during my PhD, I investigated another approach in which all processing is combined into a single block. This block performs a joint source cryptographic channel coding for secure real communication over voice channels, as stated in the title of my PhD. The joint processing can make the encrypted pseudo-speech better suited for voice channels and at the same time to be harder to cryptanalyze. During my research, however, I decided not to limit myself just to voice encrypting algorithms. Instead, I was considering the communication scheme as a whole. I wanted to know what is needed to make this scheme operational, secure, and computationally efficient. And I identified three key challenges. The first is how to send data over voice channels. For example, to exchange some configuration between the devices. The second challenge is how to robustly encrypt speech. And the third challenge is how to exchange cryptographic keys over voice channels. In this presentation, I will talk about each of these challenges. In the first part, I would like to talk about my data over voice technique. The results of this project have been recently accepted in the Journal of Wireless Personal Communications. I also presented a poster related to data over voice at the European School of Information Theory, organized by the IEEE. The biggest difficulty associated with sending data over voice channels is that voice channels are completely different than data channels. Unlike data channels, voice channels try to preserve speech intelligibility by exploiting the principles of speech production and perception. Unfortunately, there are many different objective and subjective parameters to describe speech intelligibility. Instead, voice channels try to preserve some proxy measures, such as preserving the loudness of voice, prosody, pitch, or timbre. In practice, voice channels compress speech signals to reduce the data for sending. And this speech compression could be done by a variety of different algorithms. For example, AMR is used in 3G networks, SPIX and Opus Silk are dedicated to voice over IP, and Codec 2 is designed for low bitrate radio communication. Furthermore, modern voice channels include different techniques that improve the quality of conversation. For example, voice activity detection blocks non-speech signal. Adaptive gain control changes the loudness of voice. Noise suppression removes background noise, and packet concealment reconstructs speech in the place of the lost data. All these techniques significantly change the sent signal. Furthermore, I do not have the access to the code of these algorithms. For this reason, it is nearly impossible to find a universal data over voice technique that would be compatible with arbitrary voice channels. For this reason, I decided to restrict myself just to the most popular voice channels and compression techniques. In this part of the presentation, I will talk about the voice channels that rely on linear predictive coding. LPC coders are inspired by a simplified model of speech production called the source filter model. According to the model, all voice sound is produced in vocal cords as a buzzing sound. Then, this buzzing sound is spectrally shaped when passing through a vocal tract. The movement of the tract changes the parameters of emitted sounds. In the right figure, you can see a generic diagram of an LPC speech synthesizer. The buzzing sound produced in glottis is modeled by a series of short pulses. This impulse train is then amplified to reflect different loudness of voice. Finally, the resulted excitation signal is spectrally shaped by the digital all-pole filter that models the parameters of the vocal tract. However, as we all know, not every vocal sound is produced in glottis. Some fricatives like S or F do not fit into the source filter model. For this reason, LPC coders usually include a second source of a signal and a switch between voiced and unvoiced sounds. The construction of LPC coders is suitable for vowel sounds which fit into the source filter model of speech production. And as we can see in the top two figures, vowel sounds have a harmonic structure. That is why I decided to construct my data over voice technique based on harmonic signals that mimic vowel sounds. In the first experiment, I produced a signal based on just 4 harmonics. Then I compressed this signal by a selection of voice coders: AMR, Opus Silk, and Speaks. The information I tried to send was encoded into the phase of these harmonics. In the scatter plots below, the red dots denote the constellation of phases I encoded into the harmonics, and the blue dots represent what I obtained after compressing the signal by AMR. Here we can see that AMR introduces 2 kinds of distortion. The first is a constant phase shift that could be easily compensated. The second kind of distortion resembles noise and is harder to predict. I decided to further investigate this distortion. My goal was to construct a simplified model of distortion introduced by LPC voice channels. In the left figure, you can see distortion profiles taken along this orange line. This line links the origin of the scatter plot with the sample mean of compressed simples. We may notice that these profiles have the characteristic bell shape. Some basic statistical analysis revealed that we can reasonably approximate these distortions over scatter plots by a symmetric 2-dimensional Gaussian distribution. In the second experiment, I measured the variance of distortion in every harmonic. The results are presented in the right figure. To the previous 4 harmonics, I was adding new harmonics at higher frequencies. Each time I compressed the signal using AMR, Speaks, or Opus. In this figure, the dots mark the average variance of distortion, the upper bar mark the variance of the most distorted harmonic, and the lower bar marks the variance of the least distorted harmonic. Firstly, we may notice that harmonics in a multitone signal are not distorted uniformly. And secondly, we may notice is that as we add more harmonics into a multitone signal, the variability of variance generally goes up. This and similar experiments helped me to build a simplified model of distortion introduced into multitone signals by LPC coders. Firstly, I assume that harmonics are distorted non-uniformly. And secondly, I assume that distortion over the scatter plots follows the bivariate Gaussian distribution. In the top figure, you can see the diagram of my data over voice technique. The crucial element of this technique is a codebook of pre-computed harmonic waveforms with assigned fixed indices. Firstly, the binary input we would like to send is interpreted as a sequence of codebook indices. Then, the symbol mapper reads these indices and sends a corresponding codebook waveforms. The result is a discrete signal that is a concatenation of codebook symbols, as in the figure below. On the receiving side, the receiver demodulates received codebook waveforms and decodes the indices back into the binary form. But how is the information encoded into our signal? Above, you can see a generic formula of codebook waveforms. Codebook waveforms consist of k phase-modulated harmonics. The red symbol C represents the initial phase of harmonics that encode the information you would like to send. On the receiving side, we get distorted copies of these waveforms. The role of the demodulator is to correctly decide which waveform was sent by the transmitter. Therefore, the knowledge of the voice channel characteristics would greatly help the demodulator to improve the detection rate. Here, our previous modeling of a voice channel becomes useful. Below you can see our optimized demodulation rule that searches the closest codebook waveform in terms of the Euclidean distance. The demodulator compares received symbols with all codebook symbols. It also compensates for the unequal variance of distortion and the fixed phase shift. However, these last two values must be estimated before, for example using a special training sequence. Finally, the demodulator selects the codebook waveform that gives the highest value of the following sum. The last important element is the codebook of waveforms. Intuitively, these waveforms should be as different from each other as possible. This will greatly help the demodulator in discriminating distorted signals. To simplify the process of constructing good codebooks with a large minimum Euclidean distance, I proposed another method using quaternary codes. In this slide, I will explain you this method. In our technique, codebook waveforms consists of 8 to 10 phase-modulated harmonics. Moreover, every codebook harmonic has a unique sequence of initial phases. The modulation order is 4. In the figure on the left, you can see two examples of such patterns. We can represent every such pattern by a short code word over the quaternary ring. We can think of these quaternary code words as unique identifiers of codebook waveforms. Another advantage of this representation is that we can replace a difficult problem of finding codebook waveforms with a large minimum Euclidean distance by a simpler problem, which is finding a set of quaternary code words with a large minimum Lie distance. In the table below, you can see the minimum Lie distance of some short quaternary codes. The parameter n can be viewed as the number of harmonics, and the parameter k is related to the codebook size. Large minimum Lie distance means higher robustness against distortion. However, the price for higher robustness is usually a lower bitrate. The few codes that are marked by circles denote codes mostly used by us in the experiments. Finally, I can show you some simulation results. Our goal is to obtain as low bit error rate as possible. Intuitively, this goal is achieved when the symbol error rate at the demodulator is very low. We can see in the figure that the symbol error rate decreases when the codebook size gets smaller. Furthermore, we may notice that the codebooks based on 10 harmonics outperform the codebooks based on 8 harmonics. It is because a quaternary code of length 10 can have a larger minimum distance than a quaternary code of length 8. I also tested this scheme in a real-world setting. I used two iPhone 6 and the Huawei P8 Lite, all registered to different network operators. In my experiments, I pre-computed data over voice signals and sent them over 3G networks and selected voice over IP applications. Then I analyzed the recorded received signals. In the top figure, you can see the signal sent over the 3G network. Here we may notice that real voice channels can introduce significant distortion. This distortion will lead to detection errors at the receiving site. In the bottom figures, you can see the symbol error rates at the demodulator for 3G calls and voice over IP. Over the 3G, the symbol error rate remains low when we try to send little data over the channel. However, the symbol error rate goes significantly up above 2.4 kilobits per second. This experiment shows the limit on the transmission bitrate we can achieve over the 3G networks. In the case of voice over IP, our results are much better. FaceTime and Skype, we can send data at up to 6.4 kilobits per second with a reasonably low error rate. However, Signal and WhatsApp introduce more errors so that the effective bitrate available for us is closer to 4 kilobits per second. The obtained results were very satisfactory, so I decided to test my technique for sending encrypted vocal data. In this figure, you can see my tested scheme for secure voice communication. Firstly, the input speech is compressed by a low bitrate vocoder and then enciphered by some enciphering algorithms. In the next step, we encode the data to protect against channel distortion, and we modulate the beats onto our data over voice signal. On the receiving side, the demodulator decodes the received waveforms, deciphers the binary data, and finally, the same vocoder reconstructs the initial speech. As a proof of concept, we proposed two modes of operations, low and high, dedicated respectively to 3G and voice over IP. The low mode uses transmission bitrate of 2.4 kilobits per second, while the high mode was twice faster. In both modes, voice was compressed by the codec 2 and data were enciphered by the AES in the counter mode. Moreover, the data were protected by the Reed-Solomon error correction code. In my experiments, I tried to measure the effective bit error rate of the sent encrypted vocal data. The results are presented in the right table. In every analyzed real voice channel, the obtained effective error rates were close or lower than 10 to minus 3, and they were low enough to successfully recover vocal data. In this last slide, you can see different different stages of the signal sent over the 3G network. Those who attend this defense remotely, you can access the recordings by clicking the loudspeaker icon. In the recordings I will play for you, you will hear 4 different signals. The first is the initial speech. The second signal is the encrypted data over voice signal that encodes the speech. The third is the data over voice signal received on the mobile phone. And finally, the fourth signal is the crypted speech. These signals are separated by short beep sounds. By hearing to these recordings, you may notice that the third signal was strongly suppressed after 1 second of the transmission. It is because my data over voice signal was classified by the voice activity detector as non-speech-like. However, despite the strong signal attenuation, we could still recover the encoded data. It is because the information encoded into the phase of harmonics is robust against amplitude scaling. This experiment shows that my scheme for sending data could be used for reliable communication over some real-world voice channels. Now I would like to present you the main part of this presentation, which is my distortion-tolerant speech encryption algorithm. This project was submitted to the Journal of Speech Communication. In the previous project, we tried to impose a classical engineering approach for sending data. Namely, we tried to improve the bitrate and to mitigate errors. However, this approach is really not natural for vocals. Now I would like to present the main part of this presentation, which is a new distortion-tolerant speech encryption algorithm. This project was submitted to the Journal of Speech Communication. In the previous project, I tried to impose a classical engineering approach to send data over voice channels. Namely, I tried to improve the bitrate and to mitigate errors. However, this approach is really not natural for voice channels. In this figure, you can see the same sentence sent over selected voice channels. We may notice that these waveforms slightly differ from each other. For example, the second signal is clearly played faster. Despite these differences, all these recordings sound similarly and they are fully comprehensible. Communication over these voice channels with compression is possible because the human auditory system is robust against moderate distortion introduced into the signal. We could think naively that it should be the same for our encrypted speech. Namely, I would like to obtain the following property. When I receive encrypted speech distorted by a voice channel, I would like to decrypt this signal into distorted but fully comprehensible speech. Why this approach is naive? It is because modern cryptographic algorithms do not tolerate any distortion introduced into ciphertexts, and they give two kinds of an output: perfectly deciphered data or an error. For this reason, I investigated new encryption schemes that could approximately decrypt distorted ciphertexts into distorted plaintext. And we named such cryptographic schemes distortion tolerant. So our goal is to construct a distortion tolerant speech encryption scheme. However, there is no natural representation of vocal sounds that is robust against error. That is why I was investigating new representations of vocal sounds that would fit into my encryption algorithm. After many trials, I came up to the following idea. Let's suppose that we have a representation of vocal sounds on a hypersphere. This hypersphere would be similar to this colorful sphere on the right. Let's suppose that different colors represent different sounds and that there are smooth transitions. In my idea, enciphering of sounds would be done by random rotations. For example, I would like to encrypt this sound E. Firstly, I rotate the vector and obtain a new sound A. I send this new sound over a voice channel and I receive its distorted copy. After derotating, I should obtain the sound that is similar to the initial sound E. And I perform these rotating operations sequentially, sound by sound, each time using a different rotation. It means that after encryption, our speech becomes a random sequence of sounds, and after decryption, we should restore the initial speech with some channel distortion. And if this distortion is moderate, we should be still able to understand this speech. To realize this enciphering idea, I proposed a representation of vocal sounds on the hypersphere. And I was inspired by a simplified model of speech perception. According to the model, we perceive three parameters of voice: loudness, pitch, and a so-called color of a voice, which is timbre. Loudness and pitch can be encoded by scalars. However, timbre is a multidimensional property that is roughly related to a spectral envelope. So what I did, I represented shapes of spectral envelopes using 8 parameters. Together with loudness and pitch, it gives me 10 parameters to encode a vocal sound. Later, I encode the spectral envelope as a vector on the hypersphere in 16 dimensions. Later in this presentation, I will explain how it is done. Another challenge was to construct a full scheme for scrambling spherical vectors. Before I outline you the scheme, I will introduce you into the framework in which enciphering takes place. On the left, we have the hypersphere in 9 dimensions. In the middle, there is a hyperbox P in 8 dimensions, and this space is discretized by a dense lattice. And finally, on the right, we have a flat torus, which is a composition of 8 circles, a product of 8 circles. And this flat torus lies on the 15th sphere in 16 dimensions. Firstly, let's take a non-negative vector xi with the unit norm. Then, let's define two mappings, gamma and phi, which enable transformations between these spaces. We can notice that the mapping gamma extracts spherical coordinates of unit vector x and scales these coordinates by using the vector xi. The second mapping, phi, takes as an input a vector u of length 8 and maps every coordinate of u into a respective circle. The product of these circles forms a flat torus in 16 dimensions. However, we may also notice that these circles are scaled by the coordinates of xi. We already know that xi has the norm 1. It means that every point on this flat torus has also the norm 1, and in consequence, this torus lies on the hypersphere. If we take a look at the right figure, it may seem strange how this structure could lie on the hypersphere. It is helpful to think that this flat torus is a composition of orbits that entwines the hypersphere. The transformation phi has many other interesting properties. For example, making translations over the space P is equivalent to making rotations on the hypersphere and this flat torus. Furthermore, this mapping phi transforms a dense lattice over P into a spherical commutative group code that has quite remarkable geometrical properties. Firstly, it has a simple structure, it is well distributed over the hypersphere, and finally, it is invariant to a group of rotations associated to this code. Another important property is that the mappings gamma and phi preserve the Euclidean distance approximately. Why is it so important for us? Let's have a look at the bottom inequalities. These inequalities show the distance relations between these spaces. Let's suppose that the vector phi of u is a vector that we send over a voice channel, and the vector phi of v represents its distorted copy. The distance between these two is the error introduced by the channel. Because the mappings gamma and phi preserve the Euclidean distance approximately, this channel distortion will gradually map into the left hypersphere. It means that this framework is distortion tolerant with respect to the error introduced on the flat torus. And finally, I can show you my encryption scheme. On the left, we have a vector we would like to scramble. We map this vector using gamma into the space P. We quantize the vector over the lattice and translate and scramble by a random translation. Finally, we map this scrambled vector using phi on the flat torus which lies on the 15th sphere. Here you may wonder how this framework is similar to the previous example with the colorful sphere. In fact, we can think of the right 15th sphere as our representation of different sounds. Different code words represent different shapes of the spectral envelopes. Moreover, the code words that are close to each other in terms of the Euclidean distance represent similar sounds. Finally, as I said before, making random translations over the space P is equivalent to making rotations on the hypersphere. Another advantage of this framework is that it enables a rigorous evaluation. This scheme is provably secure in the computational model. The requirement is that a sequence of random transformations used for scrambling is indistinguishable from a purely random sequence by any probabilistic polynomial time algorithm. Furthermore, this scheme is distortion tolerant because all operations are revertible and they preserve the Euclidean distance approximately. The described scheme for scrambling spherical vectors is just one element in the whole distortion-tolerant speech encryption algorithm that you can see in this figure. In the slide, I will outline you all processing steps. Firstly, the frame encoder splits the input speech into short 20 milliseconds frames and encodes these frames into a sequence of vocal parameters: energy epsilon, pitch P, and the spectral envelope D. Energy and pitch are represented by scalars, but the spectral envelope is represented as a vector on the 8th sphere. Next, the scrambling block uses a secure pseudorandom generator with a secret seed to transform the input sequence into a sequence of new vocal parameters. This new sequence is used by the pseudo-speech synthesizer to produce a harmonic wideband signal adapted to voice channels with compression. On the receiving side, the operations are essentially reversed. In the last step, a special trained neural speech synthesizer based on the LPCnet architecture reconstructs the initial speech. This scheme is fully joined because all elements are strongly interlinked with each other. The colored blocks denote the most important of these elements, and I will describe you later in this presentation. Finally, I will show you some experiment results. The first element is the speech encoder. This encoder analyzes speech frames sequentially and encodes these frames into vocal parameters: pitch P, energy epsilon, and spectral envelope D. The selection of these three parameters is not accidental. Pitch, energy, and envelope are the parameters of the simplistic speech model that assumes all voice to be fully harmonic. If we take a look at the left figure, we may notice that this model works sufficiently well for vowel sounds. Nonetheless, it is clear that encoding process removes some fine time structure of the signal and can be viewed as compression. Firstly, the speech encoder estimates speech using the autocorrelation method. On the other hand, the spectral envelope is estimated using 9 spectral windows that you can see on the right figure. The encoder computes the signal energy over these bands and obtains a set of energy coefficients, E1 to E9. Then I assume that the sum of these coefficients, denoted by epsilon, is close to the total energy of the speech frame. Finally, the vector D is obtained by normalizing the coefficients. In the last encoding step, pitch and energy are thresholded to their respective bounds, and the vector D is identified as a vector on the hypersphere. The second element is the scrambler. Scrambler takes as an input encoded vocal parameters and a bit string produced by the pseudo-random number generator. This bit string is used to produce free translations for scrambling. In the top figures, you may notice that pitch and energy are just shifted by the vectors v1 and v2. Despite the simplicity of this operation, the scrambled values are secure. The requirement is that we use a secure and properly implemented random number generator. The vector D is scrambled using our scheme for scrambling spherical vectors. In this example, the middle hyperbox P is discretized by the scaled Gaussian lattice, the densest lattice in 8 dimensions. The only difference compared to the basic scrambling scheme is that we double the value of the gamma mapping. We can do it because the initial vector D lies within the small bounded area on the hypersphere. This scrambling scheme is robust against error. This property is very useful because voice channels will likely introduce some distortion into received parameters. On the receiving side, the received values of pitch, energy, and spectral envelope will lie somewhere over these light red areas. Later, this receiving error will be mapped to deciphered values used during deciphering. Later in this presentation, we will see how the receiving error over the light red areas compares with the deciphering error over the light blue areas. The output of the scrambler is a set of new vocal parameters. Our goal is to send these parameters over a voice channel with as little distortion as possible. However, compared to the previous data over voice technique, here we can tolerate some small transmission error. Let's have a look at the top formula, which represents discrete samples of a single pseudo-speech frame. We may notice that this frame is a sum of discrete harmonic signals that mimic vowel sounds. In our encoding technique, the encoding is reduced just to manipulating the parameters of this formula. We had an idea that we could encode the scrambled vocal parameters into the homologous parameters of the pseudo-speech. For example, the blue scaling factor beta depends on the value of scrambled energy. Similarly, the fundamental frequency depends on the scrambled value of pitch. The remaining task is encoding the spherical vector back into the spectral envelope. We decided to use a bank of 16 uniformly distributed square windows that you can see in the left figure. In our technique, we encode every coordinate of D into a respective frequency band. Furthermore, this encoding takes place over the discrete Fourier transform of the pseudospeech frame and not over the power spectral density. These two changes make our pseudospeech signal less similar to real voice and more similar to frequency division multiplexing. However, the great advantage of this approach is a very efficient encoding process. The pseudospeech synthesizer produces frames sequentially and it concatenates them in the overlap and add manner, as in the right figure. Upon reception of this signal, the receiver extracts the encoded parameters and reverses the scrambling operations. In the last stage, we must reconstruct the initial speech back. We may notice that the only information we have is a sequence of distorted vocal parameters. We need a powerful tool that is able to synthesize intelligible speech based on this scarce data. In our work, we adapted the LPCnet speech synthesizer proposed by Jean-Marc Vallin and Jan Skoglund. The LPCnet is an extension of the famous WaveNet developed by DeepMind. In our scheme, we applied three major modifications to the LPCnet to make it compatible with our scheme. Firstly, we adapted the input of the frame rate network to our vocal parameters. These vocal parameters are used by the network to produce a special conditioning vector f. Our second modification is reducing the sampling rate in the second network from 16 kHz to 8 kHz. As a result, we obtained the narrowband modification of the LPCnet. My third modification is the extended dual stage training of the networks. To work properly, the narrowband LPCnet should learn how to compensate for two sources of imperfections: imperfect speech recordings and channel distortion. Because we have two sources of imperfections, we divided the training into two stages. The first stage is identical to that proposed by Jean-Marc Vallin. The training inputs are encoded vocal parameters and speech signals with artificial recording noise. Once the network learns how to compensate the recording noise, we repeat the training with channel distortion. And as we see, this distortion is introduced directly into vocal parameters. The distortion of this distribution of this distortion should reflect a typical distortion introduced by a voice channel. In the following experiments, the LPCnet was trained to the additive white Gaussian noise. I implemented this scheme in Python and made a series of experiments. In this example, I compressed encrypted pseudo-speech using Opus Silk coder to simulate the effect of voice compression by voice channels. In this figure, the horizontal axis denotes the bitrate of Silk compression. Lower bitrate means stronger compression. On the vertical axis, we have the average error introduced by compression. These errors were computed over the light red and light blue areas in the slide with the scrambler. We may see in the figures that when compression is stronger, the average error goes up. However, we may also see that the error introduced directly by compression, which is the red line, is roughly aligned with the error after deciphering, here the blue line. It means that the scheme is distortion tolerant because we could approximately decipher distorted data. In practice, our scheme should adapt to fluctuating channel conditions. I also tested the scheme in the real-world scenario. I sent an encrypted pseudo-speech signal between two iPhone 6 over FaceTime in the audio mode. In the recording that you can hear, you may listen to three signals. The first is the initial speech. The second is the encrypted pseudo-speech with distortion introduced by FaceTime. And the third signal is the crypted speech. You may hear that despite distortion introduced by FaceTime, the crypted speech is comprehensible. Finally, I made some speech quality assessment on a group of anonymous volunteers. The trials were carried online and they were divided into two parts. The first part was the speech intelligibility assessment. The results are presented in the top table. We found that the participants understood just 10% fewer words in reconstructed sentences by the LPCnet compared with the unprocessed sentences. The second assessment followed the industrial Mushra methodology. In the assessment, the participants were given shuffled recordings without any labels, and they were asked to evaluate the quality. Among these recordings, there were two hidden anchors with a standardized distortion, a mid anchor and a low anchor. We can see in the figure that the quality of speech restored from mildly distorted ciphertexts is generally fair, which is fine for a prototype. However, we may also notice that there is a positive relation between compression bit rates and the given ratings. It means that the scheme is distortion tolerant in the perceptual domain, and distortion gradually degrades the speech quality. And this was my ultimate goal. In the last part of the presentation, I would like to briefly talk about my authenticated key exchange protocol. I published the protocol at the International Conference of Information System Security and Privacy. I also gave a talk about the protocol during my stay at the Seoul National University at the research group of Professor Jung-Hae Cheon, a world-known expert in homomorphic encryption. In the previous two projects, we assumed that the sender and the receiver somehow obtained cryptographic keys. However, in real-world applications, we must define a secure way for establishing encrypted communication. In my work, I assume that Alice and Bob know each other and they can recognize each other by voice. However, I also assume that Alice and Bob didn't meet each other before to exchange the cryptographic keys. For the practical and security reasons, this exchange must be carried over the voice channel between two voice encrypting devices. We require a high level of secrecy of the cryptographic key and strong mutual authentication. Furthermore, we would like to have the protocol that is flexible and user-friendly. On the other hand, exchange over voice channels is far from being trivial. Firstly, voice channels are very unreliable. For example, the voice activity detector could block some protocol messages. Furthermore, there is no practical possibility for adding any public key infrastructure that distributes certificates to validate the user. This lack of the trusted third party poses a big risk to authentication and, in consequence, to security. In my analysis, I had to assume some model of the adversary who tries to break the protocol security. In my analysis, I assume a so-called Dole-Fiao adversary. This adversary can intercept, replay, and modify the messages. It can also perform the man-in-the-middle attack. On the other hand, I assume that the adversary has no access to the device during its operation, so that the ephemeral values are secure. In this slide, you can see the protocol interactions between Alice and Bob. In this slide, I will explain you the most crucial elements of this protocol exchange. The protocol relies on the ephemeral elliptic curve Diffie-Hellman with a flexible double authentication. The authentication relies on two different techniques: signatures and short authentication strings. Signatures provide high level of authentication, but they have a significant drawback. Namely, Alice and Bob must exchange special verification keys to validate their signatures. Sometimes it is not possible. For this reason, signature verification is not obligatory in my protocol. The second authentication mechanism are short authentication strings. These strings are short sequences of digits or words displayed on the device at the end of the protocol execution. In the left bottom figure, you can see example of such a sequence. In the diagram, you may notice that the last stage of the protocol is the vocal verification. At this stage, Alice and Bob compare their sequences vocally. And this vocal verification has a double role. Firstly, Alice and Bob challenge the voice of the peer to validate their identity. And secondly, they can detect the man in the middle if these numbers do not match. The protocol may look simple, but it is not obvious if my double authentication mechanism does not violate some security property. For this reason, I verified the protocol using Tamarin Prover, a specialized software for verifying cryptographic protocols. Tamarin verifies protocols in a symbolic model. In a symbolic model, all cryptographic primitives, like signatures or encryption, are considered perfect and unbreakable. And such analysis is still very valuable because it gives the chance to detect some logical flaws in the protocol. Such logical flaws may originate from some unintended protocol interactions, such as message replaying. The adversary could exploit these weaknesses to compromise the protocol security. Verification of protocols in Tamarin has two stages. In the first stage, we build a model of the protocol in a symbolic model, and then we define security lemmas. Verification or falsification of these lemmas reduces just to exploring possible traces of the protocol execution. In this figure, you can see a user-friendly web-based interface of Tamarin. On the left side, you can see a piece of the protocol specification. The green color denotes the verified part of the specification, and the red color denotes a compromised security. On the right, you can see a piece of the diagram built by Tamarin. This user interface helped me to build the symbolic model of my protocol and to track the errors. After the extensive experiments, I modeled the double authentication mechanism by giving Alice and Bob the freedom to authenticate themselves by signatures, vocal verification, both, or by neither of them. Moreover, I modeled the vocal verification by adding additional authenticated channel that the adversary can intercept but not modify. In this last slide, you can see the security properties verified by Tamarin in 4 authentication scenarios. The analysis focused on the following properties. Firstly, the secrecy of the current and past cryptographic keys, the mutual strong authentication, and resistance against reflection attacks and key compromise impersonation. A reflection attack is an attack in which the adversary cleverly reflects messages of Alice so that Alice finishes the protocol with herself. On the other hand, key compromise impersonation occurs when the adversary steals long-term keys of Alice and then is able to impersonate Bob or other users. In this table, we can see that without any authentication, my protocol is completely insecure. With vocal verification, we get secrecy on the session key and strong mutual authentication. With one-side signature authentication, the security goes even higher. What is interesting is that unilateral signature authentication and vocal verification are proven secure. However, this is true only under the assumption that users are honest, they abide to the protocol rules, and finally, that they can truly identify each other by voice. However, it is not always true. For example, the adversary may try to impersonate Bob by using a specialized speech synthesizer like the LPCnet. To improve the security of vocal verification, we should add some informal authentication techniques, such as contextual questions. However, the problem with informal authentication is that they are very hard to model by formal verification tools. In this presentation, I talked about the biggest challenges posed to the secure voice communication system. I described you my technique for sending data over voice channels, my speech encryption algorithm, and an authenticated key exchange protocol. The data over voice technique is adapted to voice channels using LPC-based voice compression. The technique relies on short harmonic waveforms constructed using quaternary codes. The distortion introduced by voice channels could be partially compensated by my optimized demodulation rule. Finally, I tested this data over voice technique by sending encrypted voice data over 3G networks and voice over IP. My second contribution was a distortion-tolerant speech encryption algorithm. Firstly, I presented the scheme for scrambling spherical vectors that uses spherical commutative group codes and rotations on flat tori. This scheme is used to scramble the vocal parameters of the input speech into a sequence of new vocal parameters. This new sequence is encoded into a wideband harmonic signal by my novel pseudo-speech synthesizer. In the last step, the trained narrowband LPCnet reconstructs the initial speech. I validated the scheme by sending encrypted pseudo-speech over FaceTime and by deciphering distorted signals into comprehensible speech. Finally, I validated the distortion-tolerant property in speech quality assessment on a large group of volunteers. My last contribution is a robust key exchange protocol with a flexible double authentication. The protocol has been verified in the symbolic model using Tamarin Prover. During my PhD, I gained confidence that this communication setting is technically viable. However, there are still some unresolved issues that should be investigated and verified. Firstly, my signal synchronization mechanisms are not yet robust enough for some real-world voice channels with strong jitter. Some possible solutions would be adaptive distortion compensation or some new robust technique for pseudo-speech synthesis. Another interesting research direction would be real-time estimation of voice channel parameters. This real-time information would greatly help the voice encrypting device to tune the parameters of the pseudo-speech. Finally, there is still some considerable work to be done on implementing the real voice encrypting device on a microcontroller and with 2 analog audio ports. To make this happen, we should carefully evaluate the hardware requirements and the computational complexity of my algorithms. Nonetheless, I am quite optimistic that with some additional effort, even these remaining issues can be overcome. In the last slide, you can see the list of my papers and presentations. Firstly, I presented a conference paper at the International Conference of Information Security Systems and Privacy. Also, I have an accepted journal paper at the Journal of Wireless Personal Communications. And I have another paper submitted to the Journal of Speech Communication. Moreover, I gave 2 important presentations, one at the summer school on real-world crypto and privacy, and the second during my stay at the Seoul National University. Finally, I presented 2 posters, one at the European School of Information Theory and the second at the International Conference of Information Systems Security and Privacy. That's all for this presentation. Thank you very much for listening, and if you have any questions, I will be happy to answer all of them.